Okay, welcome. Midterm's over. Woohoo! Woohoo! All right. Okay, so listen up. Let's get started on the. How is the midterm? Okay. Yeah. Okay. Okay. So. Yeah, if you have questions, I'm around afterwards. We can chat about it. Also, my office hour, I have an office hour 4 to 5 today, so you can come by and see me. If you have other issues, you can, we have the normal ways with regrades and all that stuff. We want you to, we don't want, the reason we don't open it, we don't want the stress regrade. We want you to think about your problems and your answers a little bit and look over the solutions. We do strongly believe in your right to request for a regrade because it's, to me, it's an opportunity for us to fix our mistakes when we grade. I mean, going through 900 problems is not so easy, so we make mistakes. So please help us and give us the opportunity to correct them if we did make a mistake with you. We have to be consistent, so the answer, frankly, is usually no, we have to be consistent. That's usually our answer because that's how we do it in terms of interpretation. You know, I graded the Bellman Ford problem and, you know, around number 300, I was like, well, maybe I could do it differently. But at that point, you know, it was done and it was reasonable. So, any burning questions? Okay, good. So let's go to this. So we talked about greedy algorithms. This is chapter 5. Try the obvious thing. This is the idea. What we need to do, what we need to do is prove correctness. Okay, and some of these things are a bit subtle. Okay, it's not always clear what's obvious. Okay, last time, let me remind you what we talked about last Thursday. A tree is a connected graph with no cycles. You could also, it's not just a property. In fact, this is equivalent, okay? This is an equivalent definition. A connected graph with n minus 1 edges is a tree, where n is the number of vertices in your graph, okay? It's a spanning tree in particular, okay? Sometimes we'll use the word spanning tree, meaning it's a single connected component in your whole graph. Okay, a graph is a tree if and only if it has a unique path between every pair of nodes. Okay, so all of these can be convenient, right? Because what we're doing is we're constructing a solution to a problem which will be a tree, right? So given a graph, G equals VE with edge weights defined, find the minimum weight connected subgraph. Okay, that's what we want to do. Okay, so in this definition, if you have negative edge weights, you could actually want to connect the whole graph. I mean, put in more edges than just a tree. Okay, so this definition wouldn't give you a tree unless the edge weights are non-negative. This one, you could have the edge weights be non-negative, and here you're just adding the constraint that it is a tree. Okay, you're not allowed to put in more than a tree. Okay, so for example, one is tempted to ask on the next midterm, I'm plotting my strategy, that what about max weight spanning tree? Can you do that? Okay, so this is like a reduction. Okay, and the answer is yes, you just negate the weights and get the minimum spanning tree, right? So these kind of short answer true-false questions that we ask to test your understanding, okay? Okay, so here's our example and the algorithm. So what we do in this, to find this object, in some sense, these properties are really nice. This connected tree, it's sort of all these equivalent ways of looking at it. It's sort of deeply connected to why the algorithm is so easy. Okay, so the algorithm is, well, it's just, this is really greedy. So clearly what we're doing is we're trying to connect this graph. Right now, it's not connected at all. All the vertices are by themselves. Pick a subset of edges to create a connected graph on the subset, okay? So right now, it's not connected at all. All the components are separate. Maybe I should have sort of really grayed out these edges, but now it's blue, and now you see that there's, how many components are there? There used to be some number, 6, now there's 5, right? So you can sort of see this whole process. It's just nice to sort of work through and watch it happen. Now there's 4 components, right? Every time I put in an edge, I put in an edge. I might as well, it seems to me, I might as well put in the cheapest edge. And that's the cheap edge. This one is the next cheapest edge. But that's problematic because it doesn't help me, right? I'm already, those vertices are already connected. You see the path around it, right? So meaning, I just want you to really focus and go through all the details. You see there's a path around it, right? So in some sense, when we put in 3, this edge labeled 3, the red edge, we had to check on something. We had to check whether E and B are in the same component, right? That's part of the algorithm. Here we could do it visually, but in a computer, whenever you consider putting in an edge, you have to decide whether that edge is going to create a cycle, okay? So it continues and it continues and it finishes. Okay, so here you can see again that this edge 5 created a cycle. The cycle is, you prove that there's a cycle by noticing there's a path from A to C to B of blue edges. Okay, and D, you prove a cycle because there's a path. You know there's a cycle because there's a path from D to A to C. That path from D to A to C is a thing the computer needs to figure out, right, and check. Okay, so the total cost is something. Okay, so now I'm going to review this cut property as the tree. Really, it's a consequence. I wanted to say explicitly the theorem, the definition of tree I'm using is tree has n-1 edges and is connected. That's what a tree is. Okay, I use this particular claim or lemma or definition of a tree, this property of a tree. And I'm going to prove that the smallest weight edge across any cut is in some minimum spanning tree. Again, as a cut is just a splitting of the vertices into 2 groups. S is one group, and V minus S is the other group. This is, I'm just picturing the edge or drawing the edge here, E, and I'm claiming this E is the smallest edge that connects a vertice from S to a vertice in V minus S. Okay? Does that make sense? And now what I want to argue is that it's in some minimum spanning tree. So what I first do is suppose there's some minimum spanning tree that does not contain it. Okay? If the spanning tree, just consider some minimum spanning tree. There's 2 cases. It either contains E, in which case the theorem holds, okay, or it doesn't. So now if it doesn't, we know there must be some edge that goes from a vertice in S to a vertice in V minus S. There has to be at least one edge, right? Why do we know that? We know that this minimum spanning tree is connected, okay? So we know there's a path from the endpoints of this edge through the tree. So you follow that path, and at some point that path has to leave S to get to V minus S, right? If the path goes from a vertex in S to a vertex in V minus S, at some point that path must go from, use an edge that goes from a vertex in S to a vertex in V minus S. You see? I'm being careful here, but just to make it clear, there's a couple of steps. All of them are rock solid, okay? And easy if you unfold them. Okay, so now there's a C prime that goes through here. And now what you want to do is make a new minimum spanning tree that's at least as good as this one. That's what I'm going to do as a one in all dark. That does contain E, right? I want to say some minimum spanning tree contains E. So the obvious thing here to do is to switch. Okay? So now, do I still have a tree? I removed an edge from a tree and I added another edge to a tree. That doesn't always produce a tree, right? Okay, but how do I tell this is a tree? Well, I removed an edge and added an edge, so the number of edges is the same. So if it was n minus 1, it's still n minus 1. So that first part of the definition, it still has n minus 1. Now I need to argue that it's still connected, okay, to say it's a tree. And why is it still connected? Any path that used to use E prime can now use this other path all the way around to get to between the endpoints of E prime. So any pair of vertices that was connected before, either it used E prime, the path between those two vertices used U prime, or it didn't. If it didn't use U prime, it's still connected. If it does use E prime, then it could go to E prime, it can go to its endpoint where it would have used E prime, and then go all the way around, and then go to its final destination. Right? It's like a detour. Right? Does that make sense? Okay, so therefore it's still a tree. Every pair remains connected. So now I'm using this first property to say what I've done is I've produced a new tree, and now finally what is the cost of this new tree compared to the cost of the old tree? You should all work it out yourself. Is it less? Is it more? Is it the same? Less. Because why? This is where you use it's the smallest way. We're using every bit of it, right? We're using every condition here. N minus 1, connected, the smallest. So the smallest weight edge across this cut is this. Here's E and here's E prime. Both of them are edges across this cut. So E must have weight no more than E prime, right? So therefore, the weight of this minimum spanning tree is no more than the weight of the original one. Okay? Okay, if used E, each pair remains connected because you can use this path through E, and there's n minus 1 edges, so it's still a tree, and it's no more costly because W of E is less than W of E prime. Okay? So when you study, you go home and you look at these in the slides, if you do use the slides, just make sure you understand the proof, right? Like it should be really, there should be no jump, there should be no hand waving, every step should work, right? Okay. Okay, so this is called Kruskal algorithm, the one we just ran. You sort the edges for each edge. If no cycle, you add the edge. We just proved it works because every time we add an edge, we know that thing can be completed to be a minimum spanning tree. We've always had an edge that's in some minimum spanning tree, right? And we've never created a cycle. Okay, so that cut property allows us to conclude this algorithm is correct. Okay, this is the problem. This is the one I was pointing out on the example. When you add an edge, you need to see if the endpoints are connected in the tree. So you have to have some sort of way to do that. So how do you check for a cycle for the edge UV? So what I mean by a cycle is I already have some edges I've included in the tree. And as I include them, I wanted to check if this edge creates a cycle with the ones I've already included in the object I've been growing. Okay? And what that does is now if you see the tree, then you can just do something like breadth first search in your tree edges and see if they're in the same component, for example, the endpoints. Right? That would work. Okay. The total running time for checking for a path between U and V, breadth first search or depth first search, it's a tree. It's going to do the same thing. The total running time is what? How much time does it take to do breadth first search or depth first search? Yeah, it's linear in what? What is that? Is it n? Is it the number of vertices? Is it the number of edges in the graph? It's the number of vertices in this case because the number of edges in the subset is only n. Right? Because we're only going to have n edges in our tree as we build up. Okay? So it's order n for the cycle check. Okay? So the total time is order nm after sorting. Right? You have to sort the edges, which takes m log n. Okay? Okay, does that make sense? People see? So it's pretty slow, order mn, right? We've been getting faster. So let's try to do a little bit faster. If no cycle, add an edge. So the main work here is checking for cycles, right? For each edge, once you sort them, it's m log n. That's easy. Now the work is checking for cycles. For each edge, you have to do this computation. Okay? So one other thing to notice, and for the example again, I tried to emphasize it before, is right now, what do we have? If you just take the blue edges in this, what graph do we have? the graph with a bunch of vertices, disconnected, right? How many components do we have the graph with the blue edges? Hint, there are no blue edges, okay? There's 6, right? And as I build it up, I start merging these components. So it's really kind of a merging process that happens. So as I build it up here, there's another merge of a component. As I build it up here, there's another merge of the component. And what I want to do when I'm at B, now for this edge from B to E, what I want to do is I want to check fast whether there's a path from B to E in the blue edges. I want to check that quickly. So if, for example, I could do something like maintain the names of the connected components, right? I could just check and say, oh, right now this is connected component AD, and this connected component BCE, or Bob. We can name this connected component Bob if we want, okay? And as we check, if this edge from B to E, all it has to do is say, hey, E, what connected component are you in? Bob, okay? And then ask B, hey, B, what connected component are you in? Bob, okay? So now they say, oh, this edge is inside the connected component called Bob, right? And so therefore, I can't add it. Okay, now this edge, I'm going to add this edge. What I'm going to do here, before I add this edge, I ask C, hey, what's the name of your connecting component? They say Bob. And this one, I say, what's the name of your connecting component? Alice. Oh, I can add this edge. Okay? Does that make sense? So what we want to do is we want to maintain connected components. We want to say which connected components do you belong to for any two vertices. If they're in the same connected component, they should say the same name. Okay? Typically, it's not Bob. It's typically a number, right? But, okay. Okay, and so on. Okay, so let's see. We're sorting the edges. The main issue is checking for cycle. So now we want to do this notion of maintaining the connected components in the blue graph, right? In the graph we're building up. In this tree, this forest. Okay, at first, a forest is a bunch of trees. So that's what, when I say forest, I mean it's not like a bunch of no edges is a forest. One edge is a forest. Two edges is a forest. 3 edges may or may not be a forest because they may create a cycle. Okay? Okay. So at the beginning, each node is a connected component by itself. So we'll name it the node, right? Adding an edge joins two components for sure. We never add an edge in this algorithm between two vertices in the same component, right? You see that, if no cycle. Okay, so now all we need to do, the native structure says, is edge UV in the cycle? What we say is U and V are both in the same component. Disjoint, so we're going to use this thing called a disjoint sets data structure, okay? So have you guys seen this? Have you seen union find? In 61B, do they do it anymore? Okay, good. So we'll go fast, and then you should be straightforward for a while, but it's quickly going to be math, which will make it not straightforward. Okay, so the first thing we do is we do make set. What we do for each vertex, originally, they're all in separate connected components, okay? Okay, so that's the original thing. The other one is you want to find the name of a connecting component. That's find. And then finally, you want to say, you want to put them together. When do you use the union? Okay? You use the find to say if no cycle, right? When do you use the union? Add the edge. Okay? So what this says, union says, is take the name of the connecting component, X and Y. Now for any two vertices there in those components, they would say separate names right now. So union has to somehow figure out how to make them all say the same name. Okay? So it puts them together to say, now from now on, not only will X and Y say the same name, everybody in X's component and everybody in Y's component will report the same name when we do find. Okay? So this is find just reports the names of the components. Union will represent, will write down for every vertex in this guy's component and everyone in this guy's component. Next time you do a find, they will report the same thing. Okay? If no cycle, This is how you translate the code into calls to these data structures. If no cycle, that instruction up there can be replaced like if find of u is not equal to find of v. I guess I should have had the if on both sides. Okay, if I want to add an edge, that's unioning u and v. So it's telling you that u and v's component should now be one component. Everybody in both of those components should know where they are. Okay? Okay, so how do we do this? So we maintain pointers, pi of x for each x. Make set, that's our first operation. It's just pi of x is equal to x. That's pi of x is going to be, it's a pointer structure. It's not what we actually name it, but each person has one outgoing pointer, right? So if you keep following pointers, do you eventually end? Maybe, because there might be a cycle, but so you may keep going around pointers, so you have to be a little careful. But make set, what it does is it says, what I'm going to do is I'm going to, well, I should show you what find means. Okay. So union is, what I do here is, in some sense, the pointer structure is I'm going to find x, which is going to be the name of something. And I'm going to say the parent of x is going to point to y. Okay? So what it looks like is something like this. X, each pointer points somewhere. So x's pointer points to z, and so on. Z's pointer may point to something. And the root's pointer should point to itself. Okay, I should have drawn that. Okay? Okay, so now find, all it does is chase the pointers until you find a pointer that points to itself. Okay? So now when you union two things, you know that one of them will, when you do a find, it will find the root of this data structure. It'll keep pointing pointers until it finds somebody who points to itself. Okay, so that's what happens here. In the union operation, find of x finds the root of this kind of tree. Okay? And find y also finds the root of the tree for y. Okay? So now what it does is it takes x, find x has a pointer that points to itself. It's a root. Okay? So it takes that pointer that points to itself, and instead it points to y, the root of y. Okay? So that's what's happening here. And in union, that's what's happening here. So, and find just chases the pointers until you find the pointer that points to itself. Okay? Okay, so this is the data structure. How long does it take? How long does the find take? Do you think it takes order n, order 1? Well, I mean, it depends, right? It depends on how you built the data structure, right? What the data structure did. But in this picture here, you can see that, well, maybe what happens is I joined, I union x and z, and then I union z and its parent, and then I union z and its parent, union z and its parent. That was all fine and fast. But then when I did find, I have to go over all these pointers. So it could be order n. Right? So it depends. It depends on the order of the operation. So the question is, yes, I can make now it's a little bit subtle what happens. Okay, this is where now we're no longer going to do 61B. We're going beyond. We're going to really try to understand the complexity. Okay? So the complexity here is already strange because it's like, well, sometimes it's fast. Okay, so in the worst case, it's order n. So this means we've done nothing. We've gotten no better on this cycle algorithm. But you would think that may not happen that often, right? Because you had to do all this over all the time to build up this whole data structure. It took n operations. And then one time it took order n. But maybe on average, the number of operations is small, right? So already we're like, oh, OK, well, I guess I could report the worst case time for each operation. Or I can sort of look at the sequence of operations and I say, well, there's some opportunities here, because I'm not just doing one operation. I'm doing a lot of operations. I don't care how long one operation takes. I care about how long all the operations together take. OK? Does that make sense? OK. So in some sense, intuitively, we want the depth to be small. We don't want, already this seems like a problem. Is there some choices we could have made here? to sort of intuitively make the depth smaller? What's the choice in, yeah?
Maybe instead of having it be a list of pointers, have it be a tree, like a binary tree, and then log n layers.
Yeah, he's suggesting we do a binary tree, right? Yeah, that could be, but we're going to do a little better. And we're going to do something very simple, right? Okay, so what is something we can do that's very simple? Yeah. Like here, just look at this thing. We made a choice here. We said pi of find x equals find y. Could we have done pi of find y equals find x? Does it matter which root points to who? Yeah.
You could always make the smaller connected component the child of the bigger connected component, and then you could have like all of them just point to the root or something.
Right. Okay, so he's saying we can make the smaller connected component point to the bigger connected component. So in this language, it's exactly this line that we're talking about here. He also said something else, which we're also going to do, but that we're going to do later. Okay, so I'll keep that in the bank. Okay, so find pi, I'm taking find x is really finding the root of one of these data structures. And find y is finding finding the root of this connected component, right? Or this data structure representing the connected component. So we could choose to point the root of find x's to y, or do it the other way around, right? We get a choice there, okay? And so he's suggesting we have the smaller tree, the quote smaller tree, point to the bigger tree. Okay? And that way, at least you get some notion of balance, and maybe you get this log n behavior that he was saying. Okay? Okay, so while we're maintaining pointers, we're doing this. Make it less deep. We're doing this. This code is all the same, but we're going to change the union code to use roots of x and y. Which points to which? The smaller should point to the larger. Okay? Sort of. Okay, the one problem with the smaller pointing to the larger is you may want to maintain sizes and blah, blah, blah. We're not going to actually maintain sizes. We're going to sort of have the smaller one point to the larger one. But we're going to do this with a very, very simple, just one number without trying to maintain it very hard. We never change the number. Okay? So initially, we're going to define this number called rank. The rank of x is 0. Union of x and y, what it does is it finds the root. So this find, remember, what does find do? Chase a pointer until you find a vertex whose pointer is to itself. Okay? And now what you do is if rank of r of x is less than rank of y, whose parent do you assign to whom? You want to assign the smaller guy's parent to the bigger guy. Okay, that's what this instruction is doing. It's saying if ry has a larger rank, we're going to make ry be the root of the tree that corresponds to rx. Okay? And otherwise, you're going to do it the other way. And now what we're going to also do is maintain the rank. If we don't do anything with the ranks will all be 0. So we need to like increment the rank or something, right? So here, we only increment the rank in case they're tied. If they're tied, we raise the rank of the parent. Okay? Does that make sense? That's all we do. We only raise the rank when the ranks are tied. So we're not keeping a very accurate count of the sizes. If we may not change if we have a very small tree pointing to a very big tree or low rank tree pointing to a high rank tree, nothing changes in the root. Okay? Okay. So dad's got a higher rank. This makes me happy because being a dad. Okay, so sorry. That's a lame joke. Okay, so rank of x is less than the rank of your parent. That's what this says. Okay, so pi of x, let's call it the parent. It's a little odd because the roots have themselves as their parent, but okay. So the rank of y is less than the rank of the parent. Okay? You could all, this statement actually obviously has a bug, but I'll get to it in a minute. Just in case you'd already noticed it, don't worry. So this is obvious. Why is this obvious? This is obviously true. Okay? Because the code just makes it so. right? If I ever set my parent, if I set my parent to somebody, his rank is bigger. Okay? If I set my parent to somebody, his rank is bigger. Right? It's just enforced by the code. Okay? Of course, it has to be initially true, but it's not initially true, right? Because your parent is yourself, so it's not true for somebody whose parent is themselves. Okay? If pi of x is equal to x, it can't be that the rank of x is less than the rank of pi of x because they're the same. Right? Does that make sense? You do sometimes need to look at the base case. Okay. I don't know. I must have been in a mood when I made that slide. Okay. Okay. Any rank k node really has a lot of vertices in its component. Okay. That's what that's what I'm saying with it as a big dog. It has a lot of vertices in it. Okay. So you see why? Okay, I'm going to prove it in just a second, but it's clearly going to be an inductive proof, right? Right, and it's going to be an induction that somehow uses the algorithm, right? So that's why the algorithm is up there, right? So let's look at it. Inductively, the base case is 2 to the 0. Now 0 is the rank in the base case, right? The rank of a single vertex was 0. And 2 to the 0 is greater than 1, and 2 to the 1 is greater than 1. So both are true, I think, actually. But so initially, we have a rank x. The rank of a node x is 0, right? And we have one node in the tree. And that says any rank 0 node has more than one node, right? So we're good. Okay, the induction step is when rank goes. Okay, so now we're going to look at the time. We're going to see when it happens. We're going to watch the operation of the algorithm. And we're going to say, at some point, rank x got to a k. And think about this time. Okay? So when it got to k, what was it right before that? It got to k because of this instruction in blue. Right? It could only have gotten to k when some number k bigger than 0 if it was previously at k minus 1 and it went up to k. Right? Because there's only a plus 1. Okay? So now if it was at rank k minus 1, how many vertices did it have? Can we use the induction hypothesis? Okay. So rank was k minus 1, so it has 2 to the k minus 1 nodes in this tree. But by the induction hypothesis. Okay? Does that make sense? Okay, and then we're done, right? Because what are we doing here? When this guy goes to rank k, does he get a bunch of extra children? And in that other child, what was their rank? K minus 1. How many nodes did they have in their component? 2 to the k minus 1. What's 2 times 2 to the k minus 1? So it gains the nodes from another k minus 1 node with greater than 2 to the k minus 1 nodes by the induction hypothesis. Now we used it twice. Okay? And then we can add them, and we see that adding those gives you 2 to the k nodes. Okay, it's simple. Okay? Is it clear? So it says now, if my rank is 100, I have 2 to the 100 nodes in my tree, at least. Okay? I have at least 2 to the 100. Now, did I prove that there's exactly 2 to the k nodes in the tree? Did I? Why not? I only argued at least. But is it okay? No, I didn't really prove exactly. But it could be that it's true that there's exactly, right? I didn't prove that there was not, right? But do you see a case where, yeah, here, now we can go look at the union code and we see this. If rank of R of x is less than rank of R of y, we set the parent of R of x to R of y, right? That means now R of y has more nodes and its rank didn't go up. Okay, so it could be that a tree of rank R has many, many nodes in it, but it has at least 2 to the k. Of rank 1 has many, many nodes in it, but it has at least 2 to the k. That's all we know. We don't know at most. It doesn't really matter. I just wanted you to understand. For the proof, it doesn't matter. We only care about at least. But I just wanted you to understand what we proved and what we didn't. Okay? Okay, so now find x is which one? O of log n time, O of 1 time, or O of n time? Which one do you think? O of log n, the worst case. Okay, so this one we're still not doing averaging here. We're just saying, okay, here, no matter what, we want it to be, we're going to prove that it's O of log n time. And now let's actually finish the proof. We can do it. It's also O of n time, right? Everybody know that, right? Yeah, okay, so you see that, right? It's not theta. Okay. So the rank of k node has greater than 2 to the k nodes in it. Okay? What's the total number of vertices in the whole graph? N, right? So 2 to the k can never be bigger than n, right? So if 2 to the k can never be bigger than n, k can never be bigger than log n, right? Intuitively. I'm going to do the calculation for you, but, right? If 2 to the k can't be, nobody in this data, there's only n nodes in this data structure. No tree can have more than n nodes in it. Okay, so that says no root can have a k where 2 to the k is bigger than n. Okay, so only n nodes. Every rank is so it implies that every rank is at most log n. Otherwise, 2 to the log n. That tree, if you had a rank log n plus 1 vertice, then this would be bigger than n, which is nonsense, right? Yeah. Yeah, that's one. Yeah, good question. We'll get to the runtime, right? She's asking about okay, so the rank of this tree could be 1, right? Because it's, just somehow everybody joins it, right? And so she's asking, what's the complexity of that? Okay, when you find here, how many pointers do you need to chase? How about here? No matter where you do a find on any one of these nodes, the cost is 1. What's the rank of this node? Okay, 1. Okay? So the rank is always, right? This is the one where, remember, this is, sorry, Dad's got a higher rank. Okay, so whenever you chase a pointer, you go to a node with a higher rank. So every time you do some work, you go up in rank. So you can only go up as much as the highest rank. Okay? Okay, so, but I'll say it again. Okay. So the rank is at most log n, and now your parent has a higher rank, right? So whenever you do a chaser, when you do in find, the work in find is you look at you do find of your parent, okay? And that costs one recursive call, okay? And now since your parent has a higher rank, the total amount of, the total number of calls in find is at most the total rank, because the lowest rank is 0, and the highest rank is log n, so it can only be log n costs. Okay? Only k steps in find. Okay? So, okay. Yay. Okay. Okay. Good. Oh, this is part A, apparently, of the problem. Yeah, you want to do better. Okay, which is part B, which was harder on the midterm. Okay, so, but this is going to be harder. Okay. So, okay, so so one thing about find is it's a way. Well, say I do find x and I chase all these pointers and get to R, and then I do find x again, and I'm like, oh man, I have to chase all the same pointers. What should I do instead? What's safe to do? The next time I do find x, what's its root going to be? R. What if R joins somebody else? Well, then it's going to be R's parent, right? So either way, I want to get to R. I don't want to have to go up this chain every time, right? So what should I do? Okay, so you have to chase all these things again. What a pain. So obviously what you should do is you should set your pointer to the answer. It's like next time they ask me, I know the answer, right? Next time they ask me, I know the answer. I don't need to do all this work. It's obvious, right? It's called path compression. All you do is you change your recursive call a little bit to actually store the pointer. Okay? Does that make sense? Like you got to be careful in Python because you'll run out of stack, so you should do it maybe with your own queue, but it's fine. Okay? Okay, any questions? So does this make sense? You see why this is correct? Because find x will go to R, and you're like, oh, but R could have joined somebody else. Well, now all you would have done before is go all the way up to R and then started chasing R's pointers. So wherever R is pointing, you'll just start there. You'll skip having to go through all these guys. So you might as well do this. Okay, is this better asymptotically? Can you do better than, yeah. Okay, this is not an easy proof, okay? So it's short, it's simple, and it's really not easy. So, okay. But do try to follow it, because if you follow it, that's what, I think I've always thought smarter is just making yourself do stuff. So, like this. Okay. Okay, so now what we're going to do is the union is the same. It only affects the root nodes, right? The rank properties still hold. We haven't done anything that changed the rank properties, because that we reasoned only from the text of union, right? We haven't changed the number of elements in anybody's tree. We haven't done anything like that, right? Each tree has the same elements in it as it did before. They just, instead of a long path pointing to it, all of them point directly to the root along the path, okay? Rank to parent is still higher, because what you do is you take your pointer to your parent, and you may point to your grandparent. And your grandparent is better than your parent, a higher rank than your parent. And so the rank continues to go up. It's still monotonic. Okay? And you still have greater than 2 to the k nodes in your rank k tree, because that's, you haven't changed the number of nodes in a tree. You haven't changed which trees are pointing to which. Okay? It's all inside a tree that you've changed the pointers. Okay? Now the question is, with all this stuff, now you've made it so that at least if you do one find, the next find for that one is faster. Does that mean every find is faster? Could be faster? So we can make a find take O theta of log n. Okay? So how can you do this? Do you see how you can make a find? So you do a sequence of unions to make a tree that's deep. Can you do that? Deep here is not that deep. It's just log n, right? You see how to do that? Okay, so I have to say we were discussing grading, and I was discussing grading with the TA, and the TA said, I said, well, it's an idea, and there's like, yeah, but if it's an idea you can draw a counterexample to with 3 vertices, yeah, maybe you shouldn't give it any credit. And I was like, oh, okay. So what he's pointing out is what we do. Okay, so when you have an idea, like I said before, it's fine. You have an idea, that's, you know, it has some intuition to it. Your next job is to see if you can verify if it's correct, or produce an example where you show that sort of tells you why it's not correct. Right? This is an important thing. So that's all I'm doing here. Okay, this is a little bit more complicated, but some of your algorithms, what we did is like, oh, does this algorithm work? And we just wrote down an example where it doesn't work, and then we weren't, you know, we gave you the points that were maybe not to your liking, but that's what we do. Okay, and that's what people are doing. That's how to do well, right? You come up with an idea, you see how to either make it work or see why it doesn't work. Okay, so this is all I'm doing here. Okay, do you see how to make a tree? So now I want you to be able to generate this. This is what you need to do. So yeah, so here, okay. So have you thought about it? Yeah.
Is it kind of like you never call find on any of the non-nodes?
Yeah, he's saying just don't call find, because that's not going to change your structure. So that's the answer, right? What you can do is you build a complete binary tree. First, you join these three. You say union, union, and then you join this subtree, and then this subtree. Then you join two of these subtrees, and so on, right? And you can build up a subtree that's of log n depth. Okay? Does that make sense? C, union B, C, and so on. You can build a complete binary tree, and the depth of a complete binary tree is O of log n. What we really want the data structure to look at like is this, right? We don't have any problem with lots and lots of things pointing to a single node. Okay, so we would have liked all of them to point just to the root here. It doesn't if you just do the unions this way. Okay? Okay, so this is bad. I said before, I already said the whole thing only takes log n time, and here's a find that takes log n time. But if I start doing finds on this, one find will take log n time. It'll go up here and take this path to the root, which should be many vertices. Now all of these vertices will point to the root. Now everybody over here, their depth decreased. So if you do a find on any one of these, you're a little better off, or a lot better off, right? So finds will all of a sudden clean this thing up. If you do n finds, you will get this structure. Everybody will point to the root. Okay? Okay. So now I'm going to show that over this sequence, you're going to do well. Like in one operation, you could do very badly. Not here, badly is only log n, but we're trying to do better, right? We're trying to get much better. So we're going to do m to the log star of n. So the first task here, the first difficulty here is I have to define log star for you. So let me do that. Quickly, give you a break, and then we'll come back to this, okay? So here, log star time on average. I'm putting exclamation point, but you don't know what log star is, so you're not that excited. Okay, so log star of n is the number of times one takes log to get to 1. Okay? So what's log star of 16? I don't know. Okay, let's try it out. Okay, so I guess it's C, but I should have just done it. Okay, so log of 16 is 4. So how many times did we take log? Once. Okay, that's 1. Okay, now we take log of 4 is 2. That's 2. And log of 2 is 1. That's 1. So it's 3. Right? We took log, and then we took log, and then we took log. And we did that 3 times, we got to 1. Okay? Does that make sense? Or something, okay? So 3 times. So what this says is that 2 to the 2 to the 2 is 16. Okay? So what it's asking, another way to view log star is if you took 2 to the 2 to the 2 to the 2, how many times would you need to do this to get bigger than your number? Okay? Because the opposite of taking 2 to the 2 is how many times do I need to take log of this expression on the left to get 16 down to 2, right? Every one you're pulling the exponent down, right? That's what log does. It pulls the exponent down. Okay, it's a height of powers of 2. So now log of 1 million, already, is it even worth going to log star? Well, log of 1 million is 20. And log star of 1 million is only 5, so it's faster. It's less. Okay, that's not such a big deal, but log of 1 million to 1 million. Now, 1 million to 1 million, is that a big number? That's a big number, right? Okay, so log of 1 million to 1 million versus a log of 1 million to log star of 1 million to 1 million. That's 20 million, right? That's the log of 1 million to 1 million is 20 million, and this is only 6. So log star is it grows very slowly. So log star is like very efficient, meaning it's never higher than 6, right? So it's almost linear in a sense. Really, it's much better in this theory world that I live in. It's way better than log n. Okay, let me give you a 2-minute break, and then we'll go with the analysis. Yeah.
rank was just depth. So why did you use the word rank?
No, it wasn't steps.
Depths.
Oh,
The
it's-
depths of the tree. Right?
It's not because after you compress, it won't be the depth.
That's different.
Okay, yeah.
Okay.
Does that make sense?
Yes.
Yeah. And
But
also,
without compression, it's the same.
but also, no, not necessarily. Is it always the same? Probably, yeah, it's an upper bound on the depth. I'm wondering if it's a lower bound. It's exactly depth.
I thought it's exact because you can sort of
Yeah, you're right.
constantly see that.
Yeah.
But
It's
with
inductive.
past compression, it's
Right.
different.
Right.
Okay.
That's why, because we still will use the rank.
Yes.
Okay,
Yes.
okay.
Okay, thank you.
Does that make sense? Yeah, because we're going to make a low depth tree, right?
Yes. Yes.
So
Yes.
it's not reasonable to call it depth after that because now you have a tree that's already been found on.
Yeah, if
And
we
then
do
we'll-
past compression,
It's not depth.
then it's not depth.
Yeah, right. So that's why they use the word rank.
Okay, but before past compression.
You could have used depth,
Okay.
but we're going to use the same language here.
Okay. I
Does
see.
that make sense?
Yes.
Yeah, okay. That's why they defined it. I didn't. That's how the papers define it.
I see.
Yeah.
Thank you.
Yeah. Yeah.
Because I don't see how that would be possible.
Not that one. You mean that one?
Yeah, that one wouldn't be logical.
No, no.
That one would be linear.
It'll be one order constant.
Yeah, how is that constant then?
Because, well, to do a find.
Yeah, to do a find on it, you'd have to like, in the worst case, you'd have to look through every single branch of.
No, no. All you want to do is report the root's name.
Oh, I see. Oh, and those all have like the same something connected to the root. Like they have
Yeah.
the parent involved. I see.
Yeah, yeah. Find is only trying to. All it's trying to do is, right?
Oh, I see.
Because it's just trying to say the same name for both of those. It doesn't need to know anything about anybody else.
Oh, okay. So, okay.
Does that make sense? Yeah. Okay. All right, welcome back. Let's continue. Okay, so so we're going to do this, but we already know what I'm saying here is already a little bit weird, right? I'm saying it's m log star n time. It's log star n on average, okay? We know that one of them can be really bad. It's log n, which is just infinitely worse than log star, right? It's asymptotically bigger, okay? So this seems like nonsense. I can say there is a find operation, which is terribly, takes a long time. But on average, the find operations are fast, okay? So, you know, if I do a million to a million to a million, it's 7, right? It doesn't grow. I mean, really, you can have huge objects. Well, you know, that's more than the number of particles in the universe and blah, blah, blah. But yeah, log star doesn't grow very fast. Okay. So on average. So what we're going to amortize cost. And this is a way where it's not recursion. It's not Master's theorem where you can just write a recursion. And already we've seen that in graphs where we watch everything that happens carefully. Now we're going to watch everything that happens carefully throughout the sequence of operations. Okay? We have to keep track of everything that's happening throughout the sequence of operations. Okay? So amortize. Who else amortizes? We're going to do an amortize. Who else does it? Bankers. Okay, so what do bankers deal with? They deal with money. Okay, so we're going to use a money paradigm here, right? Okay? So what we're going to do is we're going to hand out money to the vertices, okay, in our data structure, the individual nodes at points in time. We're going to give them some money. Here's some money. Spend it carefully, right? Okay. And now we're going to use it. Every time they change their pointer, they have to pay. You have to pay. I gave you some money, now use it. You changed your pointer, you have to use it. Okay? So that's the idea. So every operation, every basic operation, we're going to count. And the way we're going to count it is we're going to hand out money at some point, and then we're going to use the money up. We're going to make sure we don't use all the money up. Okay? We don't, no pointer, no vertex spends more money than they got given. And we're going to count the total amount of money we gave out. Okay? Okay, so we're only going to hand out this many dollars, and we're going to make every action that costs anything, basically you could charge everything to changing of pointers. Use it to pay for, pay for it with the dollars we hand out. Okay. Okay. So when a node becomes an internal node, its rank will no longer change. Right? We only ever update in union by rank. We only update the ranks of the roots of the nodes. Okay. So at any point in time, at the beginning, everybody's a root. Somewhere in the middle, some of the nodes are roots, and most of the others are not. Okay. The ones that are not are called internal nodes. They're not roots. And their rank, once they become an internal node, their rank forever stays the same. Okay? That's something that's important. Okay. So what we're going to do is we're going to divide the non-zero ranks into levels. Everybody who's a rank, and we're going to group them. We're going to group all the ranks, 1, not just the ranks. We're just grouping the numbers now. The rank 1 nodes. Not the rank 1 nodes, just the number 1 is a group. The number 2, 3, 4 is in a group. 5 to 16 is a group. And here, the next group will be 17 to 2 to the 16th, right? And the next one would be 2 to the 16th plus 1 to the 2 to the 2 to the 16th, right? Okay, so those are the groups, okay? So they're growing, so the number of people in these groups are growing fast, right? They're exponential of the number of people in the previous group. Okay? How many groups of ranks are there? Well, the total number of ranks is the maximum rank is log n. Right? So there's how many groups of ranks are there? Well, the max, each time you're raising, the next group is the exponent. Has exponentiates the last guy in the previous group. Okay? So the number, when do you get to say even n? It's a number to get from this group to somebody in that group, you have to take a log. So every time you go to a previous group, you're taking a log. So it's a number of times you take log to get to 1. Yeah?
Sorry, you're saying divide the non-zero ranks into levels, but what do you mean by levels?
Just into these groups. That's what I mean. I just say rank 1 belongs to the first group. Rank 8 belongs to the third group. Okay? That's all I'm saying. Those numbers are just I'm just grouping the numbers. Okay? Okay, so okay, each group grows by powering 2. So if I had the number n somewhere in here, which group would it be in? Well, you could take log of it, and that would give you a number in the previous group. And you could take log of it and give you a number in the previous group. So that would be the log starth group of that value. Okay? Okay, so now how many internal nodes ever get to rank R? Okay, so now I'm going to try to, I'm going to put the nodes in, I'm going to group them in these groups in a certain way, right? Their ranks are in a certain, the numbers, these are just the natural numbers, are grouped into these groups. Now I want to think back to the nodes in our data structure. And now how many internal nodes ever get to rank R? Should it be n over 2 to the r or a theta of n? Okay? Now remember, now think back a little bit, and we saw that anybody who had rank R had 2 to k, had at least 2 to the k vertices in their in their tree, right? So, right, when an internal node, we're talking about internal nodes now, the internal nodes get a rank R. They got a rank R, and there were 2 to the R vertices in their tree then, right? So therefore, how many people can ever achieve rank R? Well, any one can only get to rank R if it has 2 to the R nodes in its root, in its subtree, right? Now they're separate nodes, moreover, because now if one guy had 2 to the R nodes, when he became rank R, right, there were 2 guys of rank R minus 1, right? And then they got joined for him to become rank R. Now all those vertices were never in a rank R tree before, and never will be, right? Because this guy's their root. Okay, so all the nodes in the separate little trees of these guys of a rank R vertex are separate. Okay, because when they get joined, they were in rank R minus 1 vertices, they got joined. So now all the nodes in this rank R tree are those nodes. Those vertices aren't in some other rank R tree, or subtree of a rank R node. Okay? Okay, so now we're going to hand out money. To the vertices, not to you, yeah. So, okay. Is there a clock in here I just don't know about? No, okay. So we're going to hand out money to pay for the pointers and fine, the change in pointers. Okay, so every fine takes some constant amount of time plus whatever time, or you could charge it to a change in pointers. Okay? When a node becomes an internal node, its rank doesn't change. You only ever change the rank of the roots, right? When something becomes a root, you might change it, and when it gets unioned and something points to it, you might change it. Okay? So internal nodes, their ranks don't change. Okay? Okay. So now let's say for an internal node, when it becomes internal, those are the guys that are changing their pointers. The roots don't change their pointers. They know when you do find on the root or chase pointers, when you do a find on the root, it checks that it's its own parent. It stops. There's no work there. It's order 1, right? So internal nodes is who has to change their pointers. Okay, so for each of the internal nodes, when they become an internal node, they have a certain rank, and that rank will never change. Okay, that's just a number written on it. It doesn't have much meaning. It has some meaning about the past, but now it's all going to get changed because of path compression. But when that internal node becomes internal, you're like, okay, I'm sorry, you're not a root anymore. Here's some money. Okay? And this is to pay for your chasing of pointers. Okay? And now you give the ones of high rank more money. You're like, oh, okay, well, you had a lot of children, or maybe you had a lot of children, your rank is high, so we'll give you 2 to the K dollars. Okay? Okay. Okay. So now how much money do we give out? That's one thing. Okay? So we know from this previous slide there's only n over 2 to the r internal nodes of rank R. Okay, so you can just, in a group, okay, let's pick a group. Now, in the first, how many nodes are there of rank k plus 1? At most this many, right? Because now, 2 to the r, this is r, okay? And now, how many vertices are there with rank k plus 2? At most this many. How about with rank 2 to the k? At most 2 to the r, and now we're talking about r being 2 to the k. So here it's not very much. Is this a geometric series? This is geometric, right? So this total thing is O of n over 2 to the k, right? So the total amount given out in each group is O of n. There's O of log star n groups, at most, of possible ranks. Okay, so the total money you hand out is n log star n. That's it. You've handed out so much. So what? You handed out the money, now you need to make sure that that money accounts for all the work done in the finds. Okay? All the pointer chasing. right? Okay, so the cost of a find operation, I'm going to allow you to do some constant work at the beginning, plus the cost of changing pointers to pointers with high rank. Now, if you change a pointer from a parent to its grandparent, now does your parent have a higher rank than it used to? Right? Your parent had a rank, its parent had a higher rank. If you point to somebody, do you point to an even higher rank? Yeah. Okay, so when you change your pointers, there's some notion of progress. What's happening is maybe at some point, this guy pointed to this guy who had a low rank. But this guy then points up here, and this guy has a higher rank. Okay, so there's this notion of progress is where, well, my parent goes way up in rank, so I can't go up I don't have to chase as many pointers. Right? Okay, so per operation part. So now, as you do a chase of this path, I guess I've drawn a picture. Okay. Okay. When you change the pointer for a vertex, you're always changing it to a higher rank. It's actually not this picture. Okay? It's a even more complicated picture. Okay. So at some point, my parent's rank is 2, and then I change it to his parent, who might be rank 3. Later, I might get a 5. So each time the rank of my parent is going up. Okay? How many times can I go up? That's the question. That's what I'm trying to say. I'm going to bound it by bounding the number of times I go up on average. Okay? So now what I've done is every time, say my parent was in my group, and then it changed to the next group. Okay? How many times can that happen? What if it's in some group I, and it changes to group I plus 1? Well, there's only log star n groups. So the number of times my parent's rank can change groups is O of log star n. Because there's only log star n groups. And every time the rank changes a group, it can only change upward. So the number of times my parents can change groups is O of log star n time. Okay? Okay. Now the other part is, well, it could be that, say my rank is whatever, 0. And my parent is a rank k plus 1. Okay, and then I change my parent, and it becomes k plus 2. Okay, and then I change my parent, and it becomes k plus 3. How many times can I stay inside this group? Well, what's the size of this group at most? 2 to the k. Well, 2 to the k plus 1, roughly. So the number of times I can change my parent, change my rank to higher and higher is at most 2 to the k plus 1, right? Okay, so there's 2 kinds of changes of pointers. Either my parent can go up in the same group, which can happen if they happen to be in group 2 to the k, it's 2 to the k times, or they jump groups, and the number of times they jump in groups is O of log star n time. Okay. So what we're going to do, the first time we're just going to say, that's fine, it's only m log star n time total, right? Because in any find, this kind of changing can only happen log star n time. Now, for these kind of changes, we pay. We pay $1, okay? And now we want to say, we know the total amount of dollars we handed out was m log star n. So if we can pay for every operation, if the total amount of money we pay, now we've paid for every operation. Every change of pointer, we either pay for this way or we account it for that way. Okay? So there's only 2 to the k ranks in the group, maybe 2 to the k plus 1. Each node in the group has 2 to the k dollars, right? Each vertex in the group has 2 to the k dollars, right? Anybody whose rank is k, he has 2 to the k dollars, right? Okay, so that's enough money. Okay, so there's enough money to pay for all the pointer changes. Okay, so the total money is n log star n. Okay? So that's the total work done. Okay? So this kind of work does n log star n. You do order m because you may do more finds. Okay? Okay, so again, just to review, what we did is we said, look, all the work is pointers, chasing pointers. And now what we say is every time we change a pointer to our parent, we go up in rank. And that already gives us some intuition as what progress is. Our parent can't go up too high in rank. So that gives us a bound on our work. Okay? But now we say, look, some of the pointers, when they're internal, yeah. So now what we do is we hand out money to each internal node based on its rank, and we know we don't hand out too much money, and now we can charge all the work done for people coming into this group or pointing to these guys to that money given to those guys. Okay. So yeah, that's the trick. I mean, it's very short, the analysis, but it's subtle. Okay. Okay, so I mean, this is a little surprising, right? It seems like, wow, that's a lot better. But, and it's really dealing with a lot. You're dealing with a total change in the data structure and understanding that you're just not doing too much work. Okay. Okay, so some operations can be expensive, but we modify the data structure so it won't be in the future. That's the idea. Okay, and that's what path compression does. And it places credits in the data structure to pay for these modifications. Okay, okay. So the question is, can you do better? I mean, this seems pretty good. It turns out you can. Here, I got some more stuff, but this is the height of k. This seems pretty grows fast. So that what we're saying is that this inverse function, it grows very slowly. That's the intuition, right? Exponentials grow very fast. Logarithms grow very slowly. That's what happens. So we have a very fast-growing function. We take its inverse function. That's the cost of this operation. Yeah, so this is what we're doing here. Okay, so there's other functions that grow even faster. And in fact, there's MST. The inverse functions of those other functions is really the complexity of MST. MST is almost linear. Only a real serious theorist cares about this at all. But it's, there's fundamental issues about information theory and to get any better than to get it to linear. And this is an open question, whether you can do that. Okay? Okay, so now just to review, what's a cut? So what is a cut? Yeah, it's both, right? You could either define it as a set of edges in the middle that are removed. In the homework, we may define it either way. I just want to make sure that you know. It's a number, it's edges you remove. That we call that a cut sometimes. Another way to define a cut is to partition the vertices between two sets. Okay? Okay, what is the cut property for MST? I'm going to give you another MST algorithm here. Any edge in a cut is in some MST? Is that what we mean? The smallest edge in a cut is in some MST? The largest edge in a cut cannot be in an MST. It's just B, right? The smallest edge, it could be that the largest edge in the cut is also the smallest edge, right? So, okay, so now we can have, this is the proof, and now we can there's another algorithm, Prim's algorithm. So any edge of minimal weight in a cut is in some MST. If it's unique, it must be in the MST. It must be in the MST. So basically, all you have to do, you don't have to use Kruskal's. You can do other algorithms, and you'll do them in your homework. Okay, so you could add the smallest edge across a cut. So the cut property tells you this particular. So that's how did they get to better algorithms? They say, okay, let's look at other algorithms. How did they get to inverse Ackermanns? Okay, so they are, in addition to data structure work, they're also doing very different algorithms. Okay. Okay, so so this is a generic, find any smallest cut edge crossing any cut in the graph, and then you can put it in. And you keep doing that while you don't have a cycle. Now, how do you find the smallest edge? Now, how do you implement the generic one? Well, the smallest edge is order m time, but you're sort of looking at edges over and over again. So now what you have is originally you have just separated vertices, and now a cut corresponds to any connected component and the rest of the edges, the rest of the vertices. So we could do this without sorting the edges by using a priority queue, just like we did with Dijkstra. So, okay? So what we do is we started a node S by itself. That's a cut, right? S, the node by itself and everybody else. So what you can do to the MST algorithm is add the cheapest edge that's incident, right? Add the edge of minimum cost to anybody. Okay? So that's what you do. And then you keep doing that. Now you have a component of 2 nodes, and you could add the cheapest edge to anybody. Okay? So how do you maintain that? You use a priority queue, and this is all you do. For every time you pull the vertex out of the queue, you add it to the component by adding, it's already added to the component. And now for each edge, if W, if it's less than the cost, if that edge gives you a cheaper way to get to that node, you update the node's value. Okay? So, and then you use decrease key. Does it look similar to another algorithm? What's the difference? The difference here is we're not trying to compute the length of the path. So in Dijkstra, we said the cheapest path to V was C of V. So we update our path length to C of V plus weight of VW. Here we don't have the C of V. We just want to say what's the cheapest edge that connects us to the stuff we've already seen. So we don't have this one. The cheapest edge is just the cheapest edge that connects you to anybody that you've seen. Okay? Okay. Okay, so you can do it. You can do it in m plus n log n in the Fibonacci heap. Let me just see if I could cover this last thing. Okay, so I do want to say this. Okay, greedy algorithms work for something. They work for a lot of things. Okay, so this is called a matroid. They work for matroids. And matroids are set systems, which here it's edges of a graph or rows of a matrix. Now we call things called independent sets. So this same algorithm can be used, for example, to find the minimum weight basis for a matrix. Okay? So an independent set is a subset of the edges in the graph that doesn't have a cycle, right? So what's the largest independent set in a graph? What's the size of the largest independent set? How many edges can it have? N minus 1. Okay? What's the largest basis you could have in an n-dimensional space? N vectors, right? Okay, so rows are linearly independent. That's another notion of independent sets, right? That's you say, I give you a matrix, and a subset of the rows that are all independent is an independent set. That's where the name comes from. And now there's this exchange property. If you have 2 independent sets, and one independent set is larger than the other one, then there's some element in the larger one that you could add to the smaller one. Okay? So for trees, if you have a forest, because a forest is not going to have n minus 1 edges, and a tree will, there's always some edge from the tree you can add to the forest. You just use an edge that connects 2 components. Right? There are edges in the tree that you may not be able to add to the forest, but there's at least one edge in the tree that you can add to the forest. For a matrix, if you have 2 sets of rows, R and R prime, and R prime is bigger than R, you know that R spans a larger, or R is bigger than R prime, R spans a larger space. So there's always at least one of the rows in R that you could add to R prime that's independent of all the rows in R prime. Okay? So these are like matroids are fundamental things where you can find the cheapest, the minimum weight spanning tree, you can find the minimum weight basis, you can find the minimum weight many things if they have this kind of structure. And in fact, the structure is exactly the same. Okay? So it turns out that if you write the edges of a graph as this matrix, it turns out that the matrix notion of a matroid is exactly the same as Ed's notion of the matroid. Okay? So maybe I'll cover this next time a little bit. Anyway, see you.